All right. I would say let's start. I think everyone is here.
Yes.
Who has planned to attend this lecture, and thanks to Marc for setting up the video. I mean, improving the video from day to day.
If it works, let's see.
We'll see.
My laptop doesn't explode from reference.
Okay, so today's talk will be a very classical talk. So a talk coming from TAG, as I learned yesterday. So traditional algebraic geometry. It's about blowing ups. In case you know your Hartshorn, then this talk won't give you anything new, because it's I just would like to recall what is known and done classically in classical algebraic geometry, and why. Well, I mean, blow-ups are a very important topic in classical algebraic geometry, and they should really find their way into synthetic algebraic geometry to solve problems and to have examples and so on. But it's not that easy, because the blow-up construction does not commute with x, and so we may need some nice and new ideas to integrate this into the in our framework. And so the idea is just of this talk is just to recapitulate what is done classically, and then to discuss how we can integrate. So let's start with a very simple example, most classical one, which is sometimes called blowing up and sometimes called flow up. So to save some letters, I just write blow up from now on. So let's so we can construct a blow up of the affine plane in the origin. Well, and this is just the following scheme. And while this here, this works in. I write just pointwise. So we can read this as a type in synthetic algebraic geometry, and this actually works in this case here. And let's call the coordinates on A1, AN, X, and here the coordinates Y, and then we have equations like xi, yj is xj times yi. So this is the blow-up, and so what we see is that this embeds into.
Why now the coordinates of the from A n and P?
Yeah, P equals x comma y.
Yeah.
And then P is the x comma y.
Yeah. These are the coordinates of P. Yes. So this embeds here, and where we have a projection map just onto AN, which will blow up, and So here the fibers of this map are all Pn minus ones, and now let's check what are the properties of this blow up. So let's call this map phi, which is the actual blow up map. So if we remove the pre-image of the origin in AN, then it's just AN without the origin. So away from the origin, this is just an isomorphism. And well, why is this the case? If we are away from the origin, one of the xi's here is non-zero, and then we can just calculate all the yj's up to a common scalar, so we get a single point at Pn minus 1. And what happens above the origin? Well, I mean, over every point outside the origin we have just one point, but over the origin we have a whole Pn minus 1, because there, if all x's are 0, no, I mean, all these equations hold for any set of y's. Okay, so and the nice thing about this is, I mean, maybe the amazing thing when one sees this the first time is that one can see that this is smooth. So we have something smooth, but this map phi is very far from being smooth. It's just a single point, as each fiber only at one point suddenly explodes into a whole Pn minus 1. And in fact, I mean, if you, these y's here give just the ratios of these x's. So you can also write this a bit differently. So this Pn minus 1 is in fact all the lines going through the origin. And so we can also view this as these equations as an incidence equation. So a point here consists of a point in AN and a line, and this equation just says that the point here is on the line there. And then it's also this here comes here. And
so we can also say that the preimage of some arbitrary point is the set of lines through that point.
yeah, yes.
Through the origin.
And the origin, yes, because and and it's not that we just have this AN without 0 and then some Pn minus 1 sitting somewhere else. So in fact, all this is irreducible. So what's really glued into it, this Pn minus 1 and y. Well, this here is dense in X, and it's irreducible. Okay, so we can blow up the AN at the origin, and there's a nice picture for this. So let this be the origin, and now let this just be some part of the AN, and so we have lines going through this. So just visualize this as a disk, and now the blow up can be viewed as kind of staircase above this. So I just write down these lines individually, without giving them such a common intersection, so more like a staircase. The first line, and then the second line, the next line. I cannot draw this. So it's
We should start with a vertical.
yeah. So okay, so this line here is now the Pn minus 1, and now I draw every line here again, but every line corresponds to a point on the Pn minus 1, and I let this line I draw here intersect this Pn minus 1 exactly at the point that corresponds to this line. So the next line will be something like here, and then the next line will be, say, here, and then here, and then here, and at some point I have to glue here this point with this one, because after 180 degrees I'm back. So a much better version of this is famous sketch in Harshon. So it's really like a staircase. You just go with a line up and glue, and this also shows you somehow why it works. It can happen that it's smooth. We can blow up a little bit more, namely if Y is a closed subvariety in AN, and the origin is in Y, we can also blow up Y at the origin. And how do we? So what is the blow up of Y in the origin? It's let's call this Y tilde. And what we do is the following: we just take Y without the point. Now we take the pre-image, and which still looks like Y without the origin because of property 1. But then we view this as something living in X, and now we take the closure. And this is called the blow up of Y. I will see in a moment an example how it works. And if we want to blow up Y somewhere else, not in the origin, then we can use some linear transform of coordinates in AN and move our point to the origin. So this shows us that we can blow up actually any variety, because we can embed this variety at least locally into some AN and do this construction. Of course, now we can ask whether there's a better construction, that does not use coordinates, because now we can ask, because we have to ask now is this independent or not. We'll see this in a moment, but let me do an example first. Let Y be the nodal curve y squared minus x squared x minus 1. So picture here is, so we have this polynomial has double 0 at 0 and 1 0 at 1. Sorry, that's maybe. Right. So here I have a double 0. And so this is how Y looks like. And now the idea, so if I blow up the plane, so here's my Y, and now if I blow up the plane, and then I can find Y here just by removing the point, because then I have a one-to-one correspondence. So I have something like Y here. So, but when I come back along a different direction. So we'll cross this Pn minus 1, also called the exceptional divisor, somewhere else. And this we can, so this is, this one here now is, so this is Y, this is Y tilde, and let's see how we can. Okay, now so this is in A2, and now my coordinates in A2 are called X and Y, so I have to choose new coordinates for Pn minus 1, so let's call them, say, U and T. So, so the equation of the blow-up, this is given by xu equals the same as yt. So u and t are both homogeneous coordinates on Pn minus 1, so on P1, and x and y are these coordinates. And now to understand how this blow-up looks like, I have to cover my P1 with two standard charts. So let's consider the chart where t equals 1. In this case, u becomes an affine parameter for my P1. So in this case, we have y is xu and u is affine. So I can replace in this equation y by xu. So we get x squared u squared minus x squared x plus 1. And here I can factor out x squared and get some smooth quadratic here.
Minus 1.
Minus 1.
Yeah. Okay. Now, now what does x squared being 0 mean? Well, if x is so, I mean this is 0 when x is 0 up to a nilpotent. So and then y is also 0. So this is here. This being 0 is really the case where we are over the origin. And so this is exactly this P1 here, this equation x squared equals 0. Or to be more precise, this is double P1 because x squared being 0. And the rest here, this here is the equation of the red curve. And well, in the equation I get this extra factor here, which I don't get with this geometric construction, because this construction says take away the origin first. And when I do this, yeah, well, this goes away. Okay, and then and we already see why the blow-up is important. First of all, I mean this 2 tells us something about the singularity of the curve, namely it passes twice through the origin. So we get 2 copies of our exception divisor here. And we also, I mean this is now smooth. So we really separated these 2 directions. So it's like looking at the origin through a lens. And well, sometimes when singularities are more complicated, we have to choose 2 lenses, I mean blow up in succession. And the more we do, it's like looking at first, second, third order infinitesimal neighborhoods in this geometric construction. So this is
Could you draw a picture of this smooth thing that we have now?
well, this here. I mean, this is the equation. It's,
Yeah, I mean, if I look at this as an affine equation.
Yes.
So okay. So in some sense, it's the same as my original curve, but the singularity vanished.
Yes, because I mean this is just what you call parabola in school.
Right. Okay. Good.
Yeah, and of course we have to check the other chart as well, but it's not. Yeah, and what? Yeah, okay. So maybe just one more thing. So when x is 0, and you look at this equation, then then u can be plus or minus 1. And these are exactly these 2 points where this line crosses. And of course, because ut are the homogeneous coordinates of P1, so the ratio is exactly the slope of the tangent here. So it's really like analyzing this very near this point. Okay, so this is so this is very classical. And well, we can do this in synthetic algebraic geometry, I mean, just by writing these equations.
Yeah, only the closure in the general definition.
Is, yeah. There we have, yeah. And this, I will come back to this problem. Yeah, the closure is one problem, and yeah, and then we saw this yesterday in your talk, Ingo. I mean, here we have to pull out some factors of x exactly made to calculate the closure. And the question is how many? I mean, is there a common n? Yeah. Okay, but now let's do this in a modern way. I mean, not as modern as SAG, but as modern as Hartshorne algebraic geometry, where we don't use, I mean, so I mean here we really have a problem. I mean I have to show a lot. Yeah? I mean if it's not if I have to show that glues and that's independent on linear transformations and so on. So let's take a different approach. So now let's start with the Noetherian scheme. Okay, so this is a typical Hartshorne prerequisite. I didn't work out to see where I can loosen this assumption, because for our cases, I mean, we will be looking at something which is more or less looking like a scheme of finite type, and it won't be a problem for us. Okay, so X in the Noetherian scheme, S, quasi-coherent sheaf of OX algebras. So, by which I mean quasi-coherent as a sheaf of OX modules that happens to have a structure of an OX algebra, and we want to be graded. So S decomposes as a direct sum of homogeneous pieces, and the grading is compatible with the algebra structure. And we would want a bit more, namely the degree 0, we just want to have OX, and as an algebra will be generated by S1. Okay. And generated because it's a sheaf means locally generated. So what we would expect. Okay, now we can do the following construction. First of all, we define S of U, where U is just some open in X to be the sections over U, and for our cases now U will be some affine open, and then S of U becomes a graded algebra, and we can do the usual Prosh construction on S of U, and yeah, because S is an A algebra, this Prosh construction gives a morphism on to the spectrum of A, so to U. And let's call this morphism pi U. And as S is quasi-coherent, I mean, taking sections over affines commutes with localization, and so all these constructions here glue to some scheme over X, which is called then the relative prosh. So this glues to prosh for underline S pi of X. And so this is just the prosh construction, the usual one, and we know that the usual prosh construction comes with an invertible line bundle O1. So I have O1s here, and all these O1s they glue to one O1 here. So I have a line bundle on prosh S. Okay, so maybe it's, so this is the construction that works in this situation here. And maybe can be a bit more concrete by, well, but if you restrict to some affine again. For those maybe who are not that familiar with the usual prosh construction. Okay, so special case. Let's say that so if S of u, so let's say we have a special case, so we are on the spectrum of A, and S is S of X in this case, so I just take global sections of S. Let's say it's finally generated as an, so S0 is OX, so this is A, as an A algebra in degree 1, because we want S to be generated by S1, and now let's just assume that we have finitely many generators. So what is this S of X then? Well, then S of X is some homomorphic image of a polynomial ring over A, where x1 to xn are all elements, mapped to elements of degree 1. So, yeah. So this has here some kernel, and of course, our situation would like I to be finitely generated. Okay, so this is the situation we would have in synthetic algebraic geometry, and well, now what is the prosh of our S here? Well, this construction here is functorial, so we get that this prosh of S sits inside the prosh of this polynomial ring, and we already know what it is. It's just the ordinary Pn, or Pn minus 1. So this here is just the Pn minus 1 in this case, which is prosh
Should I see the connection to blow-ups yet, or?
No.
Will you come? Okay.
Yeah, and this is just the first step. And the and we have, I mean, here we have equations, and we just have to lift the equations to this prosh and then get this, and this is just cut out by the equations I. Okay, so this we can do in synthetic algebra geometry as well. Now, maybe this S is not determined, so this is a nice observation following lemma. So, so I can start with S and get this prosh. But if I know prosh, I don't know S. So it's but when I take this O1, I have a little bit more of the information. So let L be an invertible sheaf. And now let's twist our S by L. So S prime is S twisted by L. And this means that in degree D, we would like this to be S in degree D tensored by the dth power of L with the obvious algebra structure. And then we can consider the relative prosh of S prime together with the O1 bundle. And we can consider the relative prosh of S with the O1 bundle coming here. And these two here are isomorphic. And we get a canonical isomorphism, which takes okay, under this isomorphism, the pullback of O1 is not this O1 here, but then I have to put an L here, so I have to twist it by L. So I pull back L and tensor everything with L. So the idea is if I and this over X. So the idea is that if I want a different O1 here, a different means something that I would like to change this by something that comes from X. I can do this by twisting the algebra.
So the star means tensor product.
This one?
Yeah, level-wise.
Level-wise, but in this degree, because otherwise you have a hard time to multiply.
Okay.
Just a quick question regarding that example with the blow up, which was then turned smooth. Does it also hold in characteristic 2?
No. I mean, there you have. I mean, you cross the same point again.
Mm-hmm.
Yeah, I should say. Yeah, I mean, without outside characteristic 2 and maybe 3. Yeah, I mean for P large enough. Okay, let's do another example. So how do we get these S's? So let's let E be a locally free sheaf, finite rank, if you want. Then we can construct an algebra of it just by taking symmetric powers of E, and we call the relative prosh of this SP of E, called the projectivization of E. And well, if you do this pointwise, then E is just a vector space, say, or free module. And then this is just a polynomial ring. And taking the prosh of this polynomial ring just gives you projective space, the projective space over the fiber. And in fact, all constructions we've done so far are commute with base change. I mean, this is the construction of the relative prosh. So this is just I replace every fiber by its projectivization. This is what PE does. And well, in fact, we can also we can view. I mean, if you want, you can view this also pointwise. So if you have a say k-valued point on X, then you get a real algebra. I'm just a K algebra over it, or a sheaf of K algebra, and then you just take the Euler-Prosh construction with this graded K algebra. And this will then be the fiber of this relative Prosh. So this is not a problem for synthetic algebraic geometry. And this P and from the universal property of the projective space follows the universal property of PE, or the other way around, as you. So we can ask, so let Y be an X scheme, and we can ask for maps from Y into PE, and these are the same as, well, on PE we have this line bundle O1, because it's a Prosh, and we can pull back this line bundle to Y, so we get a line bundle on Y. So this is the same as pairs of a Y together with a line bundle, so Y over X again. Together, now so let's call this not G, let's call this G. So here over X I have this bundle E, so I can pull it back to Y, and I choose a surjection onto L. Okay, so this is, yeah?
So is this surjection datum or just merely existence?
It's a datum. Sorry. Well, but yeah, you have, but no, so yeah, you have to divide out isomorphisms. So maybe classically, just take a look at the kernel. So yeah, good. And so why is this the case? So let's say X is a point, when E is say just a vector space. Then here you have rank 1 quotients of the vector space, which are the same as hyperplanes, and these give points in the Pn. Okay. Now let's come to blow-ups. Now let J be a coherent sheaf of ideals. And so what is a coherent sheaf of ideals? Well, locally over spec A is just given by an ideal I. I mean finally generated. Then we can define, just take now powers of J and take the direct sum. And this obviously becomes an algebra. And often you find something like t to the d here, so just some formal variable to keep track of in which degree you are. Because I mean, if I just write down an element of j to the d, I don't know whether I mean this element of sitting in j to the d or j to the d minus 1 or whatever. So just get an algebra. And again, we have, I mean, this is just for x. And this is obviously generated by j, so by S1. So we can do the Prosh construction. And this has a, so a tilde, the relative Prosh of S is the blow up of x with respect to j. So this is our general definition. And so where does j comes from? Well, such a coherent sheaf of ideals was more or less the same as a subscheme, closed subscheme. So if y is just the vanishing of j, y is called the center. So in the example above, at the very beginning, x was a2 and y was just the origin. Let's write down this example again. Y being just the origin, then x is, in this case, x is the spectrum of A. A is just a polynomial ring, say, or a field. And the ideal is just given by xn, x1 to the xn. Now what is x tilde? Well, now we are over an affine, so I can just take the usual Prosh of S, and S is the algebra just given by powers of the ideal I. So over the affine, just can replace all sheaves by rings or ideals or modules. So S is just direct sum. And now we have to understand what this S is. So let's take the following map phi. So we have the polynomial. So A is the polynomial ring, and now I have n further generators. I consider these lying in degree 1, just by mapping yi to xi, and I think of these living in degree 1. And in this case, we can calculate the kernel of phi, which is just given by all these, so generated by all these equations. And this exercise, you can do this by hand. And well, now it's now what is now Prosh of S? Well, as we have a surjection here, Prosh of S sits closed inside prosh of this one, but prosh of this one is just the usual Pn minus 1 over A, so Pn minus 1 times An. And, well, the equations, how prosh of this sits inside here, are just given by the kernel. And now, so we see we get our blow up back from the beginning. And now the problem is, I mean, here we can do this in SAG, but the problem is calculate the kernel in general. In other words, given this description here, or maybe this here for some ideal I mean, how do I find generators and relations? So this we can, and the underlying problem is the following. So if we have a morphism of schemes, and say we have a sheaf of ideals on Y, we can ask, does it introduce this sheaf of ideals on X? So what we can do is just, or we can take the pre-image sheaf, so topologically, and not for Y, J, and well, this gives elements in OX, and we can take the ideal generated by it. So let's call this J prime, and this is called the inverse image ideal sheaf. But this is not the same as taking the usual pre-image as a sheaf of modules, because this here is given by f minus 1j tensor O x over OY. But while I have a monomorphism from J to OY, I usually do not have a monomorphism from here to OX, because the tensor product is in general not left exact. So I get something together with a map to OX, but in general it's not a monomorphism anymore. So all I can do is just take the image, and this is what happens here. So this is the image in OX. And this is, you can also see that this is the difficulty that shows up, because I mean this is here not, here we have an example where something does not commute with base change. I mean this construction does, but not taking the image. Okay. I will give some.
What was defined in this definition?
The inverse image ideal sheaf.
Okay.
The inverse image ideal sheaf is somehow you take the tensor product and you force it, and then you factor, so you get a monomorphism again. So, I have the following proposition. So let pi of x tilde to x, let this be the blow up of x in J, then we can consider the inverse image ideal sheaf, just pi minus 1 of J times x tilde, and this becomes invertible. And this is a very important case when ideal sheaves are invertible. Because then they are, well, the same as locally free of rank 1, so they are just locally given by just one, generated by one section. And the zero, so the vanishing set of this ideal sheaf is just where this section vanishes. So the subscheme defined by such an invertible ideal sheaf is just something which is locally defined by one equation. And also the other way around. So one regular equation. And when something is defined just by one regular equation locally, then it comes from such an invertible ideal sheaf. And all these sub-schemes are called Cartier divisors. And this is, this is of course much easier to work with such a sub-scheme than just with a general one, because this is just, so to speak, just codimension 1. And B, if Y is the vanishing of J, so where we blow up, and U is just X without Y, so if I remove the center, then pi, when I restrict to the pre-image of U, to U is an isomorphism. So as with the normal blow up, so the simple blow up. Okay, maybe let's do quick proof. So locally, O1, so this is just an invertible sheaf on our Prosh construction. This we know from the affine Prosh construction. So this is, and we know how it looks like. This is the module, the sheaf of modules associated to this module as you twisted by 1. So this just means that this is an algebra. I can use it as a graded module, and I shift now the degree by 1. So this is just okay, but this here is nothing. This is the ideal generated by J in S of U. And so here we come back to this J tilde. So this is basically the idea of A. And well, what about B? Well, over U, we have that J over U is just O, O of Y, also O of U, because over U, I have a non-vanishing section, and so what is now the pre-image of this? Well, this is just the prosh of, and now I can replace J by O. And now I have one copy of this for each degree, so I just add this formal variable t here. So this here is really my direct sum. Yeah, but prosh of this, I mean of A1 is just a point. This fiber-wise, so this is U. Okay, and now one can ask why are we doing all this blow-up stuff? Well, it has a universal property. So maybe one can then, this is why we do this construction. Namely, what we see here in this proposition is that the pre-image of this ideal sheaf, which geometrically is just the pre-image of the blow-up center of Y, this becomes an invertible sheaf. And this and the blow-up is the minimal way of achieving this. So, proposition.
If you blow up A to the end at 0, is that only? Oh no, you make it one dimensional in the minimal way. Okay.
Yeah.
Yeah.
So when we have A2 with a point, the origin, then this is of codimension 2. So it's very far away from being a Cartier divisor.
Yeah.
And if we blow this up, we replace it by something which is codimension 1. Codimension 1. And the rest is unchanged.
And the pre-image of the center in the blow-up will always be of codimension 1. That is the intuition.
Yes. Yeah. So instead of ideal sheaves, we can always talk about sub-schemes. Then we take a look at pre-images of sub-schemes. And so maybe So when we try to translate everything into a synthetic algebraic geometry, we have to maybe want to make some choices. Let this be the blow up with respect to J, and if now F from some other Z to X is a morphism such that when I take the pre-image of J along F is invertible, there exists a unique J from Z to X tilde such that this diagram commutes. So this is what the blow-up actually does. Okay, so the proof is not very hard. I mean, but it would take 5 minutes, and as I'm running out of time, I will skip the proof of this. Maybe you can just write down some corollary here. So let's assume we have some functoriality due to this. So assume that we have an x, that we have a blow up here, x tilde an x, and let's say we have a y here, and now we have a blow up center. so given by a sheaf of ideals. And now now we can take the inverse image ideal sheaf and get a blow up center in Y. And then we can blow up here. And then by the universal property, we get something here uniquely. So let's call this, say, H. And let's blow up this in Z. And we have to blow this up in H to the minus 1 Z. Well, this is defined using the inverse image ideal sheaf. So we get some functorial thing here, and even more is true. So if one takes a look at the construction, if Y sits inside X as a closed subscheme, this will be a closed immersion again. And
So in particular, Y could be our singular curve inside
yes,
the plane things.
yeah. And then we get like the ad hoc construction from earlier was taking a point away and taking closure, we get this back. Now, so problem is, say, if I blow up this, so if this is X and this is my center of the blow up, then I have to replace this two-dimensional, two codimensional point by something which is one-dimensional, which I can just do. But now let's take a base change of the whole situation. And the base change, say, looks like this. I just embed this as, say, second coordinate being 0. And now, if I blow up this, nothing changes because this is already Cartier divisor. And this is related that this is far from being flat, and by taking this, by calculating the inverse image ID sheaf, I really have to take the image inside of the tensor product. Just project away something. And this is again related to how to calculate this kernel. Maybe one last thing. If you're not used to relative prosh or relative spec, maybe you would like to think affine E, it's enough because one can do all the construction over an affine base as I did, and then just glue, and so and there the blow up of, say, spectrum A over I of spectrum of A. So this we had, this was just the prosh of and this sits somewhere inside our Pn, depending on the number of generators we need for this I, and the biggest problem is just to calculate this kernel to see that this is a nice scheme. And now we can ask, how does so let's come back to let's come back to our nodal curve here. Now if I blow this up, this curve looks, after blowing up, looks like this. And I have this point here splits in 2 points. So what I said about the magnification glass. And now the question is, so how can I see these 2 points? Well, these 2 points corresponds to going at the fiber here. And now, how do we calculate the fiber? Well, so we just have to pull back everything here over spectrum of A mod I. And, well, pulling back means tensoring, but everything is this here is the Frosch construction is compatible with base change. This is okay. So we see that the exceptional divisor, so what sits above, this is then spectrum of A mod I over spectrum of A of this blow up. Well, and this just, I have just to tensor this to, with A over I. So this is just Frosch of I to the D over I to the D plus 1. After tensoring. And now this here, so if I don't take the Frosch, but take the spectrum, then this has a name. This is the normal cone of y in x, so this is the center. And what is the normal cone? Well, it's exactly what we see here, it's this cone. These two lines. And when I projectivize this, I just get 2 points. So if we would like to analyze the singularity, say, or this, you can also try to understand this construction here, because it gives us a, it shows us how it looks infinitesimally around this point. Yeah?
Sorry, can you repeat where do the 2 points arise from the?
So the spectrum here is just the scheme corresponding to these 2 lines. I mean, if you want, you can do this calculation, the break. And now when we projectivize, I mean, every line becomes 1 point. So here we see these 2 points. So the exceptional divisor is really the projectivization of the normal cone, which is more or less like the infinitesimal neighborhood, the first order infinitesimal neighborhood of our subscheme inside the big one. Yeah, so, and now the question is how to make sense of this in our finitely generated context and of this.
For me, I think the most important point is making sense of the closure.
Yeah, I mean, it's all related, yeah.
But here we don't see the closure anymore, right? So we saw taking the closure of the pre-image in the beginning, but then after that you did more abstract things.
Well, we can still take the closure. I mean, to calculate this, it's the same as taking the closure. Because I mean, you can just go away from the exceptional divisor, and then so so if I is finitely generated, we can embed everything again here in the situation that we understand, namely x being just a to the n, and z being just some point, for example, yeah, and and then we can calculate this here again by this closure operation. I mean, we had similar things when we talked about properness. That it is about the existence of a best closed approximation.
To some subset.
Huh?
To some subset.
To some subset. And the same we have here, the same problem. So we have some subset. Now the question is, can we take a closure of it? So can we write down finitely many equations? And we can, this is, I mean, in the only example I gave completely, namely the blow up of a point, where we could write down these equations. But in general, here I have infinitely many. I mean, I can write down all these relations, and then, yeah. Then the question is, can I take the closure?
So what you mean is that it's always possible to define the blow-up synthetically, but the question is it a scheme?
Yeah. I mean, you can, or we can write down this, right?
I think so.
I mean, have the idea. I mean, forget about that. I is finite. Is a finite generator. Just take some I. Then you have a ring.
R algebra, you mean?
Yeah, an R algebra. And now for the prosh. Yeah, you can try to do the same gluing construction. So you take all the generators in degree 1. And all generators in degree 1 will give you an affine patch of this prosh. So you invert these. Then you take the spectrum, and then you glue. I don't see. But then you take the spectrum of something which is not finitely generated.
It's definitely not a scheme.
Yeah. So it's not what we want. Okay. Yeah.
So I wonder what this technical closure means algebraically. So if you have something non-closed, it means that subscheme that you want to close. It means that we might have some something inverted in the coefficients, maybe that if that's the equations of that thing, right? And now taking the closure would mean we need to get rid of the denominators of that equation.
Yes, and in a minimal way. So this was, I mean, the same as in Ingo's talk.
Yeah.
Where it was not clear to what power of x we need.
So that is that sort of the most general problem already? The power that we don't know, or
I feel like that's it.
I mean, you can. I mean, the point is when you have. Okay, so if I give you some subset, we can try to find the closure. Say like A1 without the origin in A1. But this construction does not commute with base change.
I have trouble relating these two.
Well, now you just take A1, and now you just restrict to the fiber over 0. Then the closure becomes empty because the set you want to close is empty after base change. So we can, So there's, So maybe what Ingo told us yesterday helps. I mean, it's. I mean, you talked about propositions, and now we would like to have some kind of nabla construction. Or nabla,
Extending nabla on all types is not difficult.
Yeah, I mean, I don't remember, but I'm not sure yet whether this is what we want.
Not sure what we want.
Yeah, so what is a nabla scheme? So maybe it's or maybe we need. I mean, for some things it does work. I mean, for the blowing up of the point in AN it works, and also I mean we can also synthetically blow up our nodal curve, and many other examples. So maybe we, just like properness, maybe we should put some extra condition like that in these situations, closures do exist.
I mean, in the affine context, we always have a candidate for the closure, namely the vanishing set of the ideal of functions vanishing on the subset under consideration.
This is finally generated.
No, it's an abstract definition, and then in special cases one can check whether it happens to be a scheme, and the only requirement for that is finite generation.
I mean, yeah, so to be a closed subset needs finitely generated.
Exactly.
I mean,
Yeah.
Yeah, I mean, is this the same as saying that we take the intersection of all closed subsets sitting above and ask whether this intersection is
Yeah, good question.
closed?
I don't know offhand.
what's this saying?
Perhaps it is.
But maybe it's too. So maybe both things are too strong. I mean, could be that could it be that let's say so I have some subset V, and now I take the closure of all closed subsets where Z sits over V. And so maybe this is not closed, but could it be that there is a closed Y, which of course is inside here, such that every other closed subset sits over Y? And if this was, or this is the case, then this is condition too strong to us.
So I mean, closed subsets correspond to finitely generated ideas, but arbitrary subsets don't correspond to arbitrary ideals. So there might be a mismatch between taking the section of subsets and taking, what is it, the section of a union of ideals. So I think.
Well, it's putting the generators together.
Right, so union of ideals, sum of ideals, yeah. Okay, yeah, good question. Can we have a subset such that the intersection of all closed subsets containing it is not closed, but there is a smallest closed subset that contains it?
Okay.
I mean, that's the generic closure from that thing, you have to find the closure of. But that's what the problem is concentrated.
Maybe let me make one last remark. Taking the closure, as you said, both crucial thing. It's also, I think, the most interesting thing to develop, because when you really want to think synthetically, because I mean here, this looks, I mean, when I draw the picture, it's clear what I mean by the tangent or the tangent cone, which is the same as a normal cone here. And we would think of this as a kind of limiting process. But this does not this does not look like a limiting process. I mean, it's really an algebraic process. So what I really would like to do is to take the equation here and scale it. So that yes, but there again the problem is, I mean, I can do this for this equation and scale it, and then I see at some point it's linear, but I have to divide out some power of x. And now the question is which power. So it would be nice to have to be able to define limits of families of algebraic varieties or schemes in our sense, just by taking the family over P1 without infinity and then taking the closure at infinity, and then being able to define this tangent cone really as a limit. And for this we really need the closure. I mean, it's the same in this calculation, so it's I think. we are going in circles.
So you want to take the limit of affine variety, I mean, embedded in the affine space. Not the limit of abstract schemes, but the limit of closed subschemes of fixed schemes.
Yeah, this would be, yeah, this is one, yeah. Okay. Yeah, and yeah, okay, maybe you should have a break.